So Jensen's inequality then says, if you have a convex function, the expected value of f of x is going to be greater than or equal to f at the expected value. And the reason is, you can think of the left-hand side as being, when you think about an expected value of function values, intuitively, so let's say we have here's a convex function, and I have a random variable x who takes values down here. And when I look at the function value, which are up on this curve, and I take an expected value of them, in each step, I'm in effect doing linear combinations of them according to the probabilities of the x's. And because it's convex, in effect, the function value ends up being above. Whereas if I take those probability weights on the x's, which I'm doing on the right-hand side, I end up with the point expected value of x, and it'll be below that value. This inequality, Jensen's inequality, it can be visually apparent. When a function has two derivatives, it's easy to prove using a Taylor series, and we won't do that. But just to say, if a function is concave, which means it has a negative second derivative, this inequality just switches. So it's quite easy to use. First example is if x is binomial. So x can only take on values a and b, and they have probabilities p and p prime. The expected value of f of x is just a weighting of f of a and f of b, and f of expected value is this. So the inequality, Jensen's inequality, is just a restatement of convexity. In other words, if I have a binomial random variable, Jensen's inequality is simply a restatement of convexity for the particular probabilities p. Another example are options. Payoff functions of puts and calls are convex. They're not smooth, but they're certainly convex. They satisfy, they're not differentiable. Well, they're not differentiable, of course, at the corner, but they're differentiable elsewhere. It's apparent that this is a convex function in the sense that if I take any 2 points and I join them, the graph of the function never goes above that secant line, that segment. So I have a graph of a put and a call, and what this tells me is that the expected value of a call, and think of now P being the risk-neutral probability, that the expected payoff under the risk-neutral probability, this would say it's going to be greater than or equal to the exercise value of the call at the weighted stock price, the risk-neutral stock price. So this says that the payoff, because remember, if I let P be the risk-neutral probability, this is almost the option price. It's not quite. In order to be the option price, I need a discount factor, and then I get an option price on the left. The present value of the risk-neutral expected payoff is the price of the option, and that's telling me that Jensen's inequality says that for a put or a call, the price of the option is going to be greater than the present value of the option exercised at the average stock price, where that average is again calculated with P star. So here's another application of the, you're always going to pay more than assuming that the risk-neutral probabilities applied to S, calculating that average S, and then substituting it into the payoff function.